This is our second video looking at distributions of random variable, and the distribution we're looking at in this video is the geometric distribution. This is our overview slide, which we'll spend about 5 minutes going over before we go back and talk about these topics in more detail and with more examples. The first thing we cover are Bernoulli trials and distributions. So when an individual trial only has two possible outcomes with a value of 1 if it is a success with probability of p, and a value of 0 if it is a failure with probability 1 minus p, it is called a Bernoulli random variable, and the trial is a Bernoulli trial. The mean of the Bernoulli random variable is p, the probability of a success, and its standard deviation is square root of p times 1 minus p. We then define the geometric distribution as how many trials it takes for a Bernoulli variable to observe a success. The probability of the first success in the nth trial is 1 minus p to the n minus 1 times p. You'll notice this 1 minus p is the probability of failure, and you have n minus 1 failures before you finally have a success, and that's this probability p. The mean of the geometric distribution is equal to the expected value of the geometric distribution random variable x, and it's equal to 1 over p. The standard deviation is square root of 1 minus p divided by p squared. In general, the probability distribution for a geometric variable decreases exponentially fast, and this is the graph that kind of illustrates that in this example. This example we will cover in the main part of our video, but we'll go ahead and take a look at it in the overview. So suppose we are at an insurance company and need to find a case where the person did not exceed his or her deductible as a case study. If the probability a person will not exceed her deductible is 0.7, and we are drawing people at random, what are the chances that the first person will not have exceeded her deductible? What about the second person? The third? What if we pull n minus 1 cases before we find the first success, i.e. the first success is the nth person? In this case, we had two random variables. Our first random variable I'm going to name y, and that's our Bernoulli trial, where we're pulling files at random, or we're pulling people's records at random. The probability we have a success that we find a person that has not exceeded their deductible is 0.7. So again, our Bernoulli trial is choosing a person at random, and y equals 1, that's a success, if they did not exceed their deductible. Our second random variable now is x, and we're going to, that's the geometric distribution, we're going to count the number of trials, the number of these Bernoulli trials before our first success. So the probability that x equals 1, that the first file we draw is someone who has not exceeded their deductible, well, that's just going to be p over here. And also we should say this is equal to p, 0.07. So we're using the probability from the Bernoulli variable, 0.7. What about the probability that x equals 2? In other words, we have to draw two files before we get a success. So that means we draw a failure on the first, that is someone who has exceeded their deductible, and then we draw a success given that the first drawing was a failure. But since these probabilities here are individual trials, it's a Bernoulli, and they're independent of each other, this is just the probability of success. So I could also just note that, probability of success. So we have a failure followed by a success. So the probability of failure is 1 minus success, or 0.3 in this case. Probability of success is 0.7. So the probability we have to draw two cases before we get a success is 0.21, or about 21%. What about the probability is we have to go through 3 cases before we find our first success? That is, we have a probability of failure on the first drawing, a failure on the second drawing, and then our third is a success. So that's probability of 0.3, the failure, another failure, 0.3, and then a success, 0.7. And finally, what is the probability the first success is the nth person? That is, we're going to have n minus 1 failures. So probability of failure, n minus 1 times, and then the nth time we have success. So that's 0.3 to the n minus 1 times 0.7. A Bernoulli trial and distribution is a distribution where an individual trial only has two possible outcomes. One outcome we consider a success, and often we label that as a number 1 for success, and there's a probability of success of p. The other outcome we label as a failure. Also, sometimes we assign it the value 0, and the probability of failure, well, that's going to be 1 minus the probability of success. So this variable then, that becomes 1 or 0, depending on if a particular trial is successful or a failure, is called a Bernoulli random variable. Its mean is p, and its standard deviation is the square root of p times 1 minus p. An example is, suppose a health insurance company found that 70% of the people they insure stay below their deductible in any given year. Each of these people can be thought of as a trial. We label a person a success if their health care does not exceed the deductible with probability of 0.7, and we label the person a failure if they do not exceed their deductible in the year with probability of 1 minus the probability of success, or 0.03. Next, we define the geometric distribution, which describes how many trials it takes for a Bernoulli variable to observe a success. And the example we had, I believe in our overview slide, is suppose we were at an insurance company and need to find a case where the person did not exceed his or her deductible as a case study. If the probability a person will not exceed their deductible is 0.7, and we are drawing people at random, what are the chances that the first person will not have exceeded her deductible? What about the second, the third? And what if we pull n minus 1 cases before we find the first success, i.e. the first success is the nth person? In this case, we have two random variables. First is our random variable for our Bernoulli trial, our Bernoulli random variable. And that variable is when we choose a person, we're going to say we're successful if they did not exceed their deductible. In other words, remember, successful, we designate a 1. So choose a person y equals 1 if not exceeded deductible. So probability, and this is given to us, the probability that y equals 1 on any given trial is equal to 0.7. That's given to us right here. And now we want to know what are the chances the first person will not have exceeded their deductible, the second person, this is kind of poorly worded. I should look, maybe I just abbreviated it, but the second person meaning that the second person is the first person not to have exceeded the deductible versus the third. The third person we draw, or at random, is the first person not to exceed their deductible. So this variable, that's counting how many trials it takes before we find someone who hasn't exceeded their deductible. So this is our geometric random variable x, and that's the number of trials before our first success. So the probability that the first person will not have exceeded their deductible, well, that's just given to us by p, right? That's literally what it is. The probability a person will not exceed their deductible. Probability that x equals 2, in other words, we have to draw 2 people before we find a success. So in other words, we have a failure on our first draw, and then our next draw is a success. It's a success given the first draw is a failure. But again, since our Bernoulli trials are individual trials, they're independent, this actually just becomes equals probability of success, right? The probability of success are independent, so this doesn't really tell us, it's not necessarily a conditional probability. So probability x equals 2, probability of failure on our first draw is 0.3, and then the probability of success is 0.7, is 0.21. And again, this is just different from the probability that y equals 2 for our y equals 1 for our second person, because that probability is just equal to 0.7. This is the probability we have a failure, and then we have a success. We want both things to happen. They're independent, so we use the multiplication rule for independent events. Now the probability that x equals 3, in other words, we have to have 3 trials before the first success. That means we have a failure on the first draw, a failure on the second draw, and finally we have a success. So all three things have to happen. So it's 0.3 times 0.3 times 0.07. And finally, if it's n minus 1 cases before we find the first success, i.e. the first success is the nth person, that means we have n minus 1 failures. So I have probability of failure n minus 1 times, and then the nth time is probability of success. So that's going to give us our 0.03 probability of failure raised to the n minus 1 times the probability of success. I shrank this work down some to give us some room to put in the graph. So if we graph this random variable x, so x can have values 1, 2, 3, 4, 5, 6, 7, and actually it can go on. Theoretically, right, it could be the 100th person or the 1000th person. We have to go through 999 trials before we finally get a success. It's a very low probability that x will equal 1,000, but it's possible. But I only did the first 7 values of x here, and then I graphed the probabilities on the y-axis. So the probability that x equals 1, we said that was 0.7. Probability x equals 2 is 0.21. Probability x equals 3 is something very small. 4, it just gets tinier and tinier. So you can see the shape of this graph is an exponential decay. So in general, probabilities for geometric distribution decreases exponentially fast. And that's because of this exponent here. So some notes on our geometric distribution. The probability of the first success is the nth trial is 1 minus p to the n minus 1. Those are the first n minus 1 failures. And then times p, and this p represents the final success. The mean, which is also equal to the expected value of the geometric distribution, is 1 over p, and the standard deviation is equal to the square root of 1 minus p over p squared. It takes an average of 1 over p trials to get to a successful trial. And this is kind of what we would have expected intuitively. In other words, let's say the probability was equal to 1/2. Then we kind of expect we might need 2 trials before we see a success, and that's 1 over p then is equal to 2. If p was equal to 1/6, we kind of expect something like 6 trials, right? Like if you're rolling a die and you want to get a 1, you probably have to roll the die somewhere close to 6 times. And so that 1 over p is equal to 1 over 1/6, which is equal to 6. And the idea is the larger this is on the bottom, so in other words, the smaller the probability, then the more trials we expect. Here we have a higher probability, so we have fewer trials we expect before we have a success. And last, as we noted, the probability distribution for a geometric variable decreases exponentially fast. An example problem, the probability that a particular case would not exceed the deductible is said to be 0.7. If we were to examine cases until we found one where the person did not hit their deductible, how many cases should we expect? We have, again, our 2 random variables where y is the Bernoulli trial where we choose a person, we let y equals 1. If they do not exceed their deductible, probability of y equals 1 is 0.7. And then we have x, the number of trials before success. We want to examine cases till we find one. How many cases should we expect? That's our expected variable, or our mean of how many we expect to have to look at. So that's our mean of our geometric distribution. The mean of our geometric distribution is 1 over p, so it's 1 over 0.7, which is 1.43 cases. Our next question, what is the chance that we would find the first success within the first 3 cases? In other words, what's the probability that x is equal to 1, or x is equal to 2, or x is equal to 3? In other words, we find it on the first try, or the second try, or the third try. In this case, we know probability x equals 1 is 0.7. Probability x equals 2, that's a failure followed by a success. And probability x is equal to 3, that's 2 failures followed by a success. So probability x equals 1 or x equals 2 or x equals 3 by the addition rule, because these are mutually exclusive, right? It's either going to be x can only take one value. We're going to have our 0.7 for x equals 1, our 0.3 times 0.7 for x equals 2, and our 0.3 squared times 0.7 for x equals 3, which gives us 0.973 or 97.3%. Another way of doing this, if we're looking for the success within the first three cases, we could say, well, what if all the first three cases were failures and subtract that from 1? In other words, the answer to this question could be found by doing 1 minus probability the first three are all failures. And that's just 1 minus 0.3 raised to the third, which will give us the same answer, 0.973. For our last example, suppose a car insurance company has determined that 88% of its drivers will not exceed the deductible in a given year. If someone at the company were to randomly draw driver files until they found one that had not exceeded their deductible, what is the expected number of drivers the insurance employee must check, and what is the standard deviation of the number of driver files? Again, y is our random variable, our Bernoulli trial, and it equals 1 when they do not exceed their deductible. So probability of 1 in this case was given to us 88% of its drivers do not exceed the deductible. Now we want to know, if we're randomly drawing files, how many do we have to draw before we find one that has not exceeded their deductible? So again, we're counting the number of files before we find y equals 1. So x is our geometric distribution. And what is it? We want to know how many we expect to draw and the standard deviation of x, the number of files we're drawing. How many do we need to look at? So expected value of y is 1 over probability p, which is 1.14 files, and standard deviation is equal to the square root of 1 minus p, our probability of failure, divided by probability of success squared, which is equal to 0.3937 files. So in other words, we expect someone to have to go through, on average, which is why they're not whole numbers of files, 1.14 files, give or take 0.39 files. Using the results that the mean equals 1.14 and standard deviation equals 0.39, would it be appropriate to use the normal model to find what proportion of experiments would end in 3 or fewer trials? And the answer is no, because the distribution is not normal. Remember, the normal curve, it's symmetric, it's a bell shape, it looks like this. This is not what this distribution looks like. It's not symmetric, right? There's no other side of the bell. So this is not a normal distribution. We can't use those tables we used in the last video. So this was a short video, but let's review what we talked about. We said Bernoulli trials are trials where there's only two possible outcomes. So we generally assign the outcome of value 1 if it is a success, and the probability of success we generally call that the variable p. We give it a value of 0 if it's a failure, and then the probability of failure is 1 minus p. And it's called a Bernoulli random variable. Its mean is p, that's the expected value, and its standard deviation is square root of p times 1 minus p. So the square root of a probability of a failure times probability of a success. The next topic was geometric distribution, which describes how many trials it takes for a Bernoulli variable to observe a success. So we have this random variable here, and we have another random variable based on the Bernoulli variable. So this is how many trials it takes for the Bernoulli variable to observe a success. The probability of the first success in the nth trial then is n minus 1 failures, that's 1 minus p raised to the n minus 1, times p, that's our success. The mean or expected value is 1 over p, and the standard deviation is square root of 1 minus p over p squared. In general, the probability distribution for a geometric variable decreases exponentially fast, as in this graph here. And this example is one we had done in our overview as well as in the main part of our video. So I'm going to skip it because this video has been so short in our review. So that's it for this video. Thank you for watching.